Hello, my name is Thomas Gottron and I am presenting joint work with my brother Christian on the perplexity of index models over evolving linked data. The motivation for that work is actually quite simple. Assume that once upon a time you had some linked data over which you have built an index. Now, in recent publication, we have seen that linked data is quite dynamic and is changing and evolving over time. So if I take a look at the same data sources at some later moment in time, I will see that the data provided there has actually changed. There might be information added, deleted, or modified. So now, the question that comes immediately to your mind is, well, how suitable is that old index if I want to use it over data which has actually changed? Or to be more concrete, if I would build a new index over the changed data, how accurate is my old outdated index compared to the new up-to-date index? To be able to answer that question, let us first take a look at index models over linked data. For that purpose, I like to think of linked data to come in the format of n-quads, so a quadruple of subject, predicate, object, and context. Subject, predicate, and object, well, that is just the RDF triples which are published, so the actual information provided on the web. And the context URI, that gives you the provenance, so where has this information been published? Or more concretely, which URI could I use to look up that triple on the linked data cloud again? So if I want to build now an index over such data, there are always the same few ingredients that I would need on an abstract level. First of all, I have to define a set D of data items, so the payload of things that I'm looking up in the index. This depends on my application scenario, what I'm actually choosing. It could be the full quadruple, it could also be just a triple statement or the subject or whatever else information you are interested in your application. Beyond the data items, I need in my index a set of keys. So these are structures or information which I'm using to actually retrieve data items from the index. And for that retrieval, I finally need the last ingredient, and that is the selection function, which for a specific key tells me which data items have been associated with that. I'm talking here about abstract index models because I am ignoring some implementation details such as data structures that you would need for searching the keys or methods for efficient storage and retrieval of the data items. They're not so much of relevance to the work that we have been done here, so I can ignore them. However, let me give you a more concrete example of one of these indices and how it would actually look like. In this example, I am assuming that I have in my keys some URIs which are denoting persons. And now in the subject-based index models, I'm using these URIs as keys and I am looking up all the triple statements where this URI is appearing in the subject position. So if I would look up the URI ukop-gotron, I would get the triple statements like ukop-gotron is of type person, ukop-gotron knows another URI that is ukop-stab, and in the same way I could look up also all the information for the other URIs which I have in my keys. I could get information about Steffen Stab, my colleague Stefan Schegelmann, or about my brother Christian working at the Institute Com at the University of Darmstadt. So in fact, this example is one of the 12 implemented index models which we have analyzed in this paper. And I've put them in the category of triple-based index models because I'm using one information out of a triple to look up the full triple. So in the example I just gave you, I'm using URIs to find all the triples which use that particular URI in the subject position. Same thing I can of course do also for the predicate, and I use a URI to find all the triples using this URI as a predicate. And of course also the same for the object. Beyond that, if you look into related work of indices over linked data, you will also find indices which are working more about metadata information. So for example, you can take a look at the keywords or terms which have been used in literals to describe entities. So this means you take a look at all the literals, break them up into words and terms, and then use these terms to find all the triple statements which are published on the linked data cloud containing one particular term in the literal. In the context of linked data, you can also be interested in the context URIs. So you would like to look up for one context what triple statements have been published at that URI on the linked data cloud. Or if you want to go on a more aggregated level, you take a look at the pay level domains of the context. And so you look up, for example, which triples have been published on the pay level domain dbpedia.org. Another type of indices are so-called schema level indices. Schema level indices, they use some kind of schema level information that you can find or extract from linked data to look up instances. So one thing that you can do is you can take a look at the RDF types which are out there, and for one RDF type you can take a look which subjects or which entities have been modeled and described with that specific RDF type. To be more precise, you can also use an index which is actually using combinations of types. So instead of having just one type, you use a particular set of types and you find all the entities which have been modeled using exactly that set of types. Similar thing you can do for sets of predicates. So you've got a property-based index, which is giving you for a specific set of properties all the entities modeled with these predicates. An incoming property set is then basically doing the same things, but is taking a look at the predicates which all refer to the same object URI. If you want to go to slightly more complicated schema level indices, then you arrive at so-called extended characteristic sets that use exactly the combination of types and predicates which have been used to describe one subject URI, or you end up at our own homegrown index, schemex, which is using the types of the subjects along with the predicates associated with it and the types of the objects that these predicates link to. All these 12 index models have been implemented and are available as open source code on GitHub, so if you want to play around with it, you can take a look at those as well. The link is also provided in the paper. Okay, so now we've got the index models under control, so let's take a look how we can actually measure accuracy of the indices over evolving data. Again, just to recall, we have the situation that there is some data which we have visited some time ago, and the data has changed at a later moment in time. Now, we're having our two indexes, one over the recent data, one over the older data, and we want to compare them for accuracy. The first thing that you can take a look at are actually the key element sets. So you can compare the key elements which are used to retrieve information from the two indices and how far they have remained the same. For that purpose, you can use the Jacquard similarity, which is taking into consideration the size of the intersection of two key element sets divided by the size of the union of the two key element sets, and is giving you an idea of the relative size of the overlap. However, this doesn't tell you how accurate is the index itself. To answer that question, one idea that you could come up with is to use Sparkle queries. However, there are a few problems out there. First of all, on a practical point of view, the dataset which we later used in our experiments doesn't have any established query log, so we would have had to come up with our own Sparkle queries. But furthermore, we're also looking at very different types of indexes. For example, consider the keyword-based index, where we're looking up individual terms from literals. And in comparison, there are the typeset-based indices where we're using combinations of RDF types. Now, it is difficult to find a set of Sparkle queries which are using all these information equally likely so that you are allowed and actually able to compare the quality of the indices when answering to Sparkle queries. And finally, if you have a fixed set of Sparkle queries, you will not probably take into consideration all of the index, but just some parts of it. And so you're biased into certain directions and you're not evaluating the accuracy of the entire index. So given all these problems, we have eventually decided not to use Sparkle queries, but to get back to some structures which we have used in other publications already, and that are distributions over the data. There are two good reasons for that. First of all, the distributions are relevant to several applications. For example, in federating queries over linked data, you might be interested in the distributions over the data to estimate the size of intermediate result sets. Other applications making use of distributions are in the area of statistical schema inferencing or in computing the redundancy of schema information on the linked data cloud. And furthermore, you've got established metrics for comparing distributions. But first of all, let's take a look at how we can actually obtain a distribution from an index. So here you see again the index as I have introduced it before. You've got your keys, the selection function sigma, and this is giving you for each key a set of data items associated with that key. If now I want to get a distribution over the data, what I can do is I can simply take a look at the count information. So how many items have been associated with a key? If I know all these numbers, I can also sum them up so I get an idea of the total amount of items which have been indexed. And this allows me to use relative frequencies as a kind of maximum likelihood estimator for the probability of one specific key element by taking a look at how many data items are associated with that key and how many data items do I have in total in the index. Technically, you still have to take care of smoothing to overcome some unobserved key events that just came up later on in time after you have built your index, but for this I will refer you for details into the paper, or there is also a paper at the Profiles workshop at this conference where you will find more information about smoothing linked data indices. Okay, so now we're at the point that we can have our two snapshots of the data at different points in time, and we've got two distributions. Now we want to compare those. I've already told you there are established metrics for comparing distributions, and they're coming from the field of information theory. The most famous metric that you have in information theory is probably entropy. If you take the entropy of one particular probability distribution, then this is giving you in a certain way something that you can interpret as the expected length in bits for an optimal encoding of a randomly chosen key element in our case. Now, we are not dealing just with one distribution, but we have a distribution P, which we want to actually estimate from the distribution Q that we have seen in our index. And for that purpose, you've got cross entropy. Now, cross entropy, if entropy is giving you the optimal encoding length, then cross entropy tells you what is the expected length in an encoding if you don't know the true distribution of the keys, but just some alternative different distribution. Obviously, this will not be optimal, but suboptimal as an encoding length, and so you will get higher values here for cross entropy. Depending on how good is your approximation of the probability distribution P by the probability distribution Q, the values will be lower for a good approximation and higher for a worse approximation. The name-giving metric that we also have in the title of our paper, Perplexity, is then based on the cross entropy and is 2 to the power of the cross entropy. What does it tell you? It can be seen as the number of how many uniformly distributed keys would actually give you the same entropy value as you have observed here for the cross entropy. And that also allows you for a normalization of perplexity by dividing by the number of elements that you actually do have in your key set. And so that is giving you basically a perplexity relative to the uniform distribution over the keys if you would assume that as a distribution. Now that might seem a bit abstract, so let me give you an example of how to interpret perplexity. Perplexity based on cross entropy can be seen as how surprised are you about the outcome of a random experiment if you have some expectations. So let's do a classical random experiment. Let's assume we've got a die, and here we have an unfair die to make things a bit more interesting. So this die, if we're rolling it, we have a probability of half to actually get a value of 6, and all the other numbers are much less likely but equally likely. So now we want to model this distribution using some assumption. The easiest thing that we can do, not knowing anything, is we can assume a uniform distribution. So basically assuming a fair die here to model the unfair die. If now I compute the cross entropy between P and Q, and I compute the perplexity, I will get a value of 6. And that is not entirely surprising because it actually reflects our initial assumption, our model, of each of the sides being equally likely. So I am as perplexed as I would be for a uniform distribution over 6 events, the 6 sides of our die. And if I now take a look at the normalized perplexity, I will get a value of 1. And that is exactly the normalization effect that you have here. So a uniform distribution to model whatever other distribution will always give you 1 under normalized perplexity. And this is also giving you, in a certain way, a baseline, because you can always assume a uniform distribution. But let's take a look at how is this perplexity value developing if we're doing a better job. So, well, the best job we can do is we can really get the distribution perfectly right. In this case, perplexity is actually boiling down to the perplexity over the normal entropy. And I would get a value of 4.472, which is an absolute minimum value of perplexity that I can have. And the normalized perplexity in this case is 0.745. So as said, this is a minimal value. You will not get any better than this. Well, if we're not having perfectly the right idea, so we have a distribution which is maybe close to the one that we are actually trying to model. In this case, I'm having a die where also the value of 6 is more likely, but just at 40% and not at 50%. In this case, I will get a perplexity value of 4.8 or a normalized perplexity of 0.813. So the value is slightly higher than estimating the distribution perfectly, but it is still better than assuming a uniform distribution. Now, what happens if I get the distribution entirely wrong? Assume you have a model for that die which is actually assuming that the value of 3 is having a probability of 50% and all the others are less likely. In this case, you will get a very high perplexity of 8.5 and a normalized perplexity of 1.4, which is above 1, and in this case tells you that basically you would be better off in modeling that die using a uniform distribution. Okay, so now with these metrics at hand, let's take a look at the stability of index models over evolving data. For that purpose, just to recall again, assume we've got our data in the past, and we've got a newer version of the data. For both, we can build an index, and for both, we can get distributions, and we can compare these things using the Jacquard over the key elements or the perplexity values. For our experiments, we actually use data from the Dynamic Linked Data Observatory, which is providing you weekly snapshots of always the same data sources. For the paper here, we have used 77 weekly snapshots, and each of these snapshots contains around 16 million triples. Now, with these snapshots of the same data sources, we can start with the first snapshot, and that is basically giving you our initial old value for which we assume we have built once upon a time our index, and now the data is evolving over time steps t1, t2, t3 to tn, in our case t77. And then we can take our implementations of the index models and actually derive indices, all the 12 types of indices, and estimate our distributions for our original index over the once upon a time data and over all the steps in time how the data has evolved. If now we want to measure the accuracy of that index, now I'm doing the example of perplexity, I can take a look at the deviation of these distributions. So I can take the distribution that I have in my old outdated index and I start to compare it to an index that I would have constructed at the point t1. And I will get some perplexity value that is probably rising because the data is changing. And now I do the same thing also for a later moment in time, again using my old index to estimate the distribution over the point in time t2, and I do that for t3, and so on, until I have compared it to all the time snapshots of the data that I have, and I will get an idea of how is my accuracy developing over time, or in this case, how is perplexity evolving over time. So let's take a look at the concrete data. Now we start with the Jacquard similarity of the key set. Recall here a value of 1 is good, and the lower the value is getting, the further away you are from the original key set. Well, if we're looking at the triple-based indices, you will see that all of them are decreasing in similarity over time, pretty much at the same rate, but you see that they're at different levels, and you see that the subject keys are actually changing quicker and more than the object and the predicates in the data set that we have observed. If we're looking at the metadata-based indices, then you see also there a relatively constant decline for all of the indices, both for context, for keywords, The pay level domains, they are slightly more stable. But what gets really interesting now is when you're taking a look at the schema level indices. Because here you can see the upper two lines, that's the RDF types and the incoming property sets, they are still doing relatively good. But the other two indices, so that's the type sets and the property sets, they are decreasing more. And towards the end, they're actually having very low similarity values of around 0.2 between how the data actually looks like compared to the index that we have built at the initial point in time. And if we're taking a look at the more complex schema level indices, so the extended characteristic sets and schemax, then you see that here the situation is even worse. And already after 10 weeks, you have only this Jacquard similarity of 0.2, and towards the end, you arrive at values of 0.1 or even below. However, we said this is just the elements that you have in the key set. It doesn't tell you very much about the accuracy in estimating distributions. So let's take a look at normalized perplexity. If I take a look at the normalized perplexity of the triple-based indices, there's one thing that becomes immediately obvious, and that is that while the predicate and the object-based indices, they are having a very low normalized perplexity, the subject-based index is actually having a high normalized perplexity, and around week 55 you're arriving at the point where assuming uniform distribution would give you better values because the normalized perplexity is having a value of higher than 1. Something similar, even not to that extent, is what you can observe on the on the metadata-based indices. Now, here the keywords are very stable. You hardly see the line being down there at the 0. The pay level domains is also doing quite fine. The context-based indices, they're not doing that good. And there's one particular thing that we have observed here towards the end, this increase and burst in normalized perplexity. We could actually point that down to one of the data sources, which was all of a sudden at around week 60 starting to produce much more data and contribute much more triples to the data set. And that is actually what you observe here as the increase in perplexity. A nice thing actually was when we were taking a look then at the schema level indices, because here, both for the simpler models and also for the complex extended characteristic sets and the schemax, the normalized perplexity was very low, particularly surprising given you have the large deviation in the key sets that we have observed. Now, to get a bit more details about the well-performing indices, let's zoom in on normalized perplexity. Now we have on the y-axis only a range between 0 and 0.1. For the predicate and the object-based index model, you see that things are behaving very similar. If you're taking a look at the metadata-based index, you will see also here that still the keywords have a very, very low value. There's an explanation for this. Basically, what you're doing here is you're estimating a distribution over words in the language used to describe resources. And that is basically boiling down to a Unicron language model, which you can really assume also to be, regarding the distribution, actually quite stable over time. If you're looking at the schema level indices, there are two things that you will notice here. And the first thing is that there's a bit more fluctuation here. And the second thing is that in particular, the typeset and the property set index, they're actually quite stable under normalized perplexity. Similar thing you also observe for the more complex schema models of extended characteristic sets or schemax. So what does that mean? Given that the keys were actually diverging so a lot in our index, this means that the keys which are stable, they are actually responsible for a large part of the data, and the distribution in that large part of the data seems to be quite stable over time. Okay, so to conclude and summarize our findings, what we have done here is we have evaluated the stability of 12 linked data index models, which have also been fully implemented and are available as open source. Furthermore, we have developed this application-independent evaluation framework for measuring the accuracy of linked data indices using information theoretic metrics. And finally, in our experiments, we have observed a good stability of the schema level indices when it comes to the distributions, which is particularly surprising given that the key set actually seems to change a lot for these indices. What are our plans for future work? Well, one thing so far we always had to basically grab a full snapshot of the data to compare our old index with a hypothetical new index over the data to be able to judge the quality. Of course, in a real-life scenario, you might want to do that just over a sample of the data. So that is one of the things that we're going to take a look at. And the second thing that we're interested in is how does these things actually relate to actually answering real queries over the data. So for that purpose, now we're going to take a look in real Sparkle queries, and let's say if our observations of the distributions also align with the observations that you would get when you're really querying the indices for data. Thank you.